I want to take a few minutes to talk about formal charge and oxidation state, and a few of similarities or differences that happen between them. Recall that they're both ways to put charges on atoms, either individual or in structures, and we can use a technique called arrow pushing to help us do this. Arrow pushing is something that we use a lot in organic chemistry to show us the mechanisms of which reactions go through to produce the products that are yielded from those chemical processes. And they show the theoretical movement of electrons that help us do this. A full arrow symbolizes the movement of 2 electrons, while a half arrow symbolizes the movement of 1 electron. And we're going to use this to help us see how these electrons are distributed and how we can differentiate between formal charge and oxidation state using these structures. So we're going to start with ammonia, and we're going to start with formal charge. And remember that this is the charge assigned to an atom in a molecule, assuming that all electrons in all chemical bonds, remember 2 per bond, are equally shared between atoms regardless of relative electronegativity. So we're going to start with ammonia. And to make this a little more visual, and this whole video is going to be about visually helping you guys see and understand how these things happen and where we're getting these numbers from when we say nitrogen needs 5 electrons. How do we get there? We'll actually look at a periodic table so you can do this on your own as well. But first, we're going to do exactly what it says up here in the definition. We're just going to chop the bonds in half. Wrong color. And then we're going to put 1 electron from each bond on each of the atoms, right? So 1 on hydrogen, 1 on nitrogen. 1 on hydrogen, 1 on nitrogen, 1 on hydrogen, 1 on nitrogen. Cool. Now, we can go ahead and write down how many electrons each atom has, right? So this hydrogen has 1 electron. This hydrogen has 1 electron. This hydrogen has 1 electron. And this nitrogen has 1, 2, 3, 4, 5 electrons. Oops. Right? So, we then look at the periodic table and use our electron configuration skills from chapter 7, right? So nitrogen in group 15, remember that the electron configuration for nitrogen is 1s2, 2p3, remember 1s, 1, 2, 2s2, 2p3. Left off the 2s because I'm so conditioned to noble gas configurations. So see, when nitrogen has 5 electrons, right, on it, so those 1s electrons don't move, remember. When nitrogen has those 5 electrons on it, it's neutral, so it has a charge of 0. And I'm going to erase this because we're going to come back to different elements later, right? But nitrogen has 5 electrons, right? So how you're going to calculate formal charges is very simple, right? So you're going to take, so let's just say we're doing this for nitrogen. You're going to take the number of electrons that it needs to be neutral. Bam, 5. You're going to subtract the number of electrons that it has. Okay? Subtract the number of electrons that it has. Well, it has, remember, we said it has 5. 1, 2 from the lone pair, 3, 4, and 5. Right? So the formal charge on nitrogen is 0. Now, just a public service announcement, right? If you subtract these two numbers and it's positive, right, that's the charge. If you subtract the two numbers and it's negative, that's the charge, right? So it doesn't have plus 1 electrons. If this number was 4, and we went 5 minus 4 equals 1, it's not 1 electrons. It's a plus 1 charge, okay? So anyway, so that's the nitrogens. Let's do one of the hydrogens since they're all the same. So hydrogen needs 1 electron minus the 1 that it has is 0, right? Add up the charges, or the formal charges on each atom, 0 plus 0 plus 0 plus 0, charge is 0. So that is formal charge. That is formal charge. So now what we're going to do is we are going to do oxidation state for the same thing. And oxidation state's a little bit different, right? So we're going to read through the definition. It's the charge assigned to an element in a chemical combination that represents the number of electrons lost or gained, if that number is negative, by an atom of that element in the compound. So positive oxidation state means electrons were lost, right? So if this bond was to go to the hydrogen, that means that an electron was lost from the nitrogen. Because remember, this bond is one electron from N and one electron from H, right? So if both of the electrons go to hydrogen, nitrogen lost one electron, okay? So we'll get rid of that and we'll do the same process, but instead of cutting the bonds in half, right, the bonds are going to completely go one way or the other. One of those atoms is more electronegative. So take a couple seconds and see if you can figure out where the bonds will go. So now that you are back, we are going to talk about where these bonds are going, and I hope what you wrote is something like this. So I like to do this myself just to kind of show where these electrons are kind of cupped into. I will draw little curved lines showing where the bonds aren't going to be, right? So you should have an arrow going to hydrogen, an arrow going to hydrogen, and an arrow going to hydrogen, right? So remember, that means 2 electrons from each bond go to hydrogen. So now, when we're calculating the oxidation state, right, we're going to do that same thing from the periodic table, and since we already did it once for nitrogen, we won't do it a second time. Remember that nitrogen needs 5 electrons to be stable. Okay, we're going to subtract, right, 1, 2 electrons. Those are the only electrons on this nitrogen. Remember, for each of these bonds, there was 1 electron from nitrogen and 1 from hydrogen, and they both went to hydrogen. So 5 minus 2 gives me a 3+ oxidation state for nitrogen. Now we can do the same thing for hydrogen, right? So remember, for hydrogen, they need 1 electron to be neutral. Subtract the amount of electrons that it has. Remember, it has both of the electrons from this bond. So it has 2 electrons. So it has a -1 charge, or 1 minus charge, or just minus on those hydrogens. Now, if you looked at a table of common ions, right, you'd see that if hydrogen was in that negative conformation, it was in the hydride anion form, that it would actually have a -1 charge. So that is a good way to do this. If we add up all the oxidation states, just like we did for the formal charge, and I'll do this actual operation for you. So we need N plus 3 times H equals the charge, 3 plus 3 times 1 minus gives me 0. There's no charge on ammonia, so we are good to go. We're going to do one practice problem together, and then there's going to be a couple more practice problems that you can do on your own that I will click through so you can see them if you're not printing out a notes document for this. And then at the end of the video, like I did for the nomenclature review video, I will do a quick blurb about what the answers are so you can check your work. But we're going to start by doing this as a practice problem with the iodate anion, IO3 minus. So pause the video really quick. I'm actually going to pause my end as well, and I'm going to draw the Lewis structures in so it doesn't take a bunch of time drawing all this stuff so this video stays at a manageable length. So go ahead and draw those structures, pause this video, and then check and see if you've done it correctly. So I hope this is what you wrote down if you did indeed pause the video, which I hope you did, because this would be a great practice problem to remember your resonance structures, right? So when you sum up all the valence electrons, put your bonds in, skeletal structures, and lone pairs, you'll notice that you need to make 2 double bonds, and there should be 1 lone pair left on your iodine. So we're going to just take one of these structures and do the formal charge, since they're all usually the same. Remember, there's no selectivity as to where this single bond is and where these double bonds are. So it can be at this oxygen, or this oxygen, right? It's like we're rotating it this way. So let's just pick this middle resonance structure. We'll draw it super big so we can do our formal charge and our oxidation states. So I'm not going to draw the big bracket in, just so we have more room to draw arrows. So a little smaller here, double arrow here. So again, let's start with formal charge. So remember, we're cutting the bonds in half, and we're going to draw half arrows from each of the bonds to each of the atoms around the bond, or those atoms where the electrons came from. So we'll zoom in a little bit. We're going to have a half arrow from this bond, a half arrow from this bond. Hold on, we'll draw a little bit easier to see. Half arrow, half arrow, half arrow, half arrow. You will get the hang of this as you do it more. So remember, from those double bonds, it's 2 bonds, 4 electrons. So I'm drawing them as 2 half arrows. Contrarily, you could draw them as 1 full arrow from each bond. I want to stay consistent, however, with cutting those bonds in half and showing you that the electrons are equally shared one way to the other. So let's do these double bonded oxygens. So to write this down, I'm just going to say I double bond O to make this easier. And we'll underline the O. So this oxygen right here, right, has 1, 2, 3, 4 electrons from lone pairs. Plus 1, 2 electrons from bonding. So there's 6 electrons around it. Remember that oxygen being in group 6, whoops, pointer, 16, needs 6 electrons to be neutral. So it has 6 electrons. We'll just show the operation. 6 minus 6 equals 0. So the formal charges on both of these iodine double bond oxygens is 0. Let's do the iodine single bond oxygen. And it is a negative, so we will show that. The single bond oxygen, count with me, has 1, 2, 3, 4, 5, 6, 7 electrons around it. So we'll do 6 electrons from lone pairs plus 1 electron from bonding equals 7 electrons. 6 minus 7 equals -1, which is the formal charge on there, which is great because I've already shown that it's a -1. I like to show charges on my structures, so remember where those negative signs are coming from. It's a little reminder to you. Last but not least, we're going to do this iodine. Right? Iodine is a halogen. It's in group 17. You should know that without having to look at the periodic table. So it needs 7 electrons to be neutral to fill up that valence shell. Let's recall that from lone pairs it has 1, 2, then it has 3, 4, 5, 6, and 7. So we'll show the operations just for fun. So we have 2 electrons from lone pairs, plus we have 5 electrons. That was a really gross 5. 5 electrons from bonding is 7 electrons. 7 minus 7 is 0. And that's the formal charge on the iodine. So again, we can add up all these formal charges up and get the total charge on the molecule. Remember that the charge on iodate, IO3 minus, is 1 minus. So we're just going to total these up really quick. So we can go 0 plus 0 plus -1 plus 0 equals -1. Whoops. So now we are going to do oxidation state. And we're going to do that down here. And for the sake of the argument, we're going to do it on the same structure. Okay? Now, I'll have you know, right, there's 1 double bonded oxygen, 2 2 double bonded oxygens, 1 single bonded oxygen on each structure. So they're all going to sum up to be the same thing. It's just going to matter which one that negative is on. For the intents and purposes of this video, we're just going to do it on one resonance structure. Just so we can make this a little bit easier. So now, remember, we're going to draw the electrons from these bonds going to the more electronegative atom. Actually, no. So this is, I'll even title this here. This is formal charge. This is oxidation state. So I'm going to draw in these little curved lines to show where my bonds are going to be focused on. So oxygen is the second most electronegative atom, or element, I should say. So, and I hope you have not forgotten your lone pair on iodine, but I did. So you can always draw that in. Hopefully you catch your mistakes before it's too late. But now we're going to draw all the electrons from the bonds going onto the oxygens. So these are full arrows. They're not half arrows. So now I've drawn in my arrows. I'm going to calculate my oxidation states. So we're going to do the iodine double bond oxygen first, right? So there's going to be 4 electrons from lone pairs plus 4 electrons from bonds. Remember, 2 electrons per bond, 2, 4 is 8 electrons. Remember that oxygen needs 6. Needs 6, doesn't have 6. So this is saying that each oxygen, right, so it has 8 electrons, 6 minus 8 is 2 minus. So it's saying that the oxidation state of this oxygen and this oxygen are both 2 minus. Now we're going to do the oxidation state of the single bonded oxygen. So we're going to go I single bond O minus. So it has 6 electrons from lone pairs plus 2 electrons from bonding is 8 electrons. 6 minus 8 is 2 minus. What a coincidence. The oxidation state of this negative oxygen is also 2 minus. Now we're going to do the iodine. So not bonded to anything, just the iodine in the middle. Notice that no pushing arrows pointed to the iodine, so it's just going to have those 2 electrons from the lone pair on it. And I should zoom in a little bit more. So we'll do the iodine right here. It has 2 electrons from lone pairs, 0 electrons from bonding, so that's 2 electrons. It needs 7, it has 2. So this iodine is in an oxidation state of 5+. If we add up all these oxidation states, we'll get the charge on the overall atom, so let's do that. We have 3 oxygens and 1 iodine, so it's 2 minus plus 2 minus plus 2 minus plus 5 plus equals -6 plus 5 equals -1. Or 1 minus, however you want to say it, but there is a -1 charge on the iodate anion. So that is a walkthrough of a sample problem of how you're going to do this. And you don't have to draw in the arrows once you get the hang of it, but I like to draw them in as a reminder of where these electrons are going and how they actually fit into the picture of the difference between formal charge and oxidation state. There are some practice problems. There's sulfur hexafluoride, there is the nitrate anion, and there's the ammonium cation, so that's fun. Best of luck in doing these. You have the periodic table that's right here, so if you always go to this screen at 19 minutes and 10 seconds, you will see the periodic table. So if you need it, there it is to consult. You can also go to ptable.com. But again, these are the worked problems. Go ahead and do the practice problems, and I will come back in a couple seconds with the answers. Please try and do these by yourself first. Again, this is really important that you get this practice in before you take exams on this, and so you really internalize the meaning of oxidation state and formal charge before you get to classes like General Chemistry 2 or Organic Chemistry, both of these classes being areas where it's extremely important to be able to do these types of problems. Good luck. So now that you've completed the practice problems, I'd like to go through them briefly with you. First was sulfur hexafluoride, and this was a fun one to draw. It's a good Lewis structure review, as well as remembering what those halogens and chalcogens can do in terms of expanding, in terms of holding electrons. So, you should have gotten that the formal charge on both sulfur and fluorine are 0. The oxidation state of sulfur is 6+. The oxidation state of fluorine is 1-. And you should have written out these structures, these pushing arrows, and these calculations. The nitrate anion, I think we've done this in another video as well. I just chose to use it again because it was good practice to draw resonance structures. Let's remember, right, there's no selectivity to where this double bond is, so it can be here, here, or here. I chose these two structures just to do my stuff on because I didn't want to redraw them since I already had two structures drawn. Why would I do more? You obviously could if you wanted to. This is totally fine as well. You should have gotten that for formal charges, nitrogen was at a 1+. The nitrogen double bonded to an oxygen, the oxygen with the double bond, I should say, is at 0, and the single bonded oxygens are at 1- for an overall charge of 1-. The oxidation states would have nitrogen left at a 5+, since none of those bonds have electrons that go back to nitrogen. The double bonded oxygens at 2-, the single bonded oxygens at 2-, which should not be a surprise, since when oxygen is in its anionic form as O, or as the oxide, I should say, or as O2-, it will have a charge of 2-. Adding up all the charges gives you the charge of the whole molecule as 1-. The last example is NH4+, is the ammonium cation, of course. Half pushing arrows on the formal charge structure show that nitrogen has a formal charge of 1+. Hydrogens are all at 0, so we get an overall charge of 1+. For the oxidation state structure, remember that all these bonds are going to go to hydrogen, and the formal charge of nitrogen then would be 5+. Formal charge of the formal charge of nitrogen would be 5+, the formal charge of hydrogen would be 1-, and we would get a total charge of 1+, which is correct. I hope this video was something that helped you understand the differences and similarities between formal charge and oxidation state. Again, the practice problems are there for you to write them out and do them all as a whole so that you could kind of see what's going on. With that being said, we're going to be on to hybridization and polarity, and that should round out Gen Chem 1. See you there.